So today I'm going to talk to you about heat transfer during phase changes. Oh, that's terrible. And we have so far talked about heat transfer and how much heat is being changed during while a substance is in a specific phase. So, for example, when water is in a liquid phase, what do? Water in liquid phase, H2O. We use which equation? We use Q equals mass times the specific heat, and then the change in temperature. And when I say heat, I mean heat energy. All right. Let's look at a phase diagram that we've talked about before, and that's as we slowly heat something up, and let's heat water up. So let's say we have water at a temperature that's below 0 degrees Celsius. And this is like time over here on the bottom. So you heat this up. When you get to 0 degrees Celsius, what happens? It melts, right? This is in the solid phase. And it melts, and the temperature flattens out. We don't have a temperature change. And then, after it's all melted, it moves upward, and this is the liquid phase. This is melting. And then we get to the temperature of 100 degrees Celsius. And that's when it's going to change again. We'll boil off or vaporize. What did I do that for? Boil. And then you can, after it's completely gone, it will be in the gas phase here. Y'all remember that, right? Okay. Well, what we've done here. Okay, so if we want to heat up a liquid, say from some initial temperature to a final temperature, going from this point to this point is delta T, right? Change in temperature. And then we can find out how much energy is added during that time. If we know the mass of the substance, C delta T. This is the heating curve of H2O. And this C is 4.18 joules per gram per degree Celsius, or per Kelvin, which they show you on your reference tables. If you look on reference table B, you see these values, right? It's the specific heat capacity. And also, if you want to know what the equation is, we look on table T, and we look in heat calculations, and you can see it's the first one listed right there, with all the units with all the variables explained over here. Now, we've got two other equations in this, and those equations we're going to use when we have a phase change. And so, in this first phase change, we have Q is equal to mass times the heat of fusion. It's called, and up here, we have Q is equal to mass times the heat of vaporization. And you can see both of those equations right here. Mass times heat of fusion, mass times heat of vaporization. And to get the heat of fusion, listed right here. It's 330 joules per gram. And the heat of vaporization is 2,260 joules per gram. Notice in these equations, there is no change in temperature. Why? Because during a phase change, there is no change in temperature. You can see that it's flattened out in both of those cases. So doing these type of problems is really quite simple. If we go ahead and look, let's take a look at an example that's in this handout that I gave you. If it will load, please. How many joules are required to melt 255 grams of ice at 0 degrees? That 0 degrees Celsius is extra information. It doesn't come into the problem at all. It tells you that. It didn't even need to tell you that. We know that it melts at 0 degrees Celsius. But they put that in there a lot of times. So the knowns are the 255 grams. We know the heat of fusion from the reference table B. Simply multiply the two together, and you get the joules needed to melt the ice at that temperature. You could also do that for vaporization. How much does it require to vaporize 423 grams of water at 100 degrees C? Again, the 100 degrees C does not need to be told to you. It's extra information. Simply, again, multiply those two together. Note that it takes a lot more energy to vaporize water than it does to melt the water. A lot more energy per gram. So that is how you do this. If you have any questions, just ask me.